honorary guests, we are going to move to the last, but certainly not the least, speaker for this part of the plenary session. We have Professor Brian Yuliarto with us. Before Professor Brian Yuliarto presents his talk, I will first read his brief biography. Professor Brian Yuliarto, S.T., Master of Engineering, Ph.D. His expertise is material science and engineering. He is currently the Dean of the Faculty of Industrial Engineering, Institut Teknologi Bandung, Indonesia. He did his bachelor at Institut Teknologi Bandung, master's degree at the University of Tokyo, and also PhD at the University of Tokyo, graduated in 2005. Currently, he's conducting a number of research projects, include gold mesoporous-based plasmonic biosensor for the detection of transmittable diseases, LSPR-based detection of COVID-19 using aptamer RNA, highly porous nanomaterial fabrication for biosensor application, development of advanced metal oxide as toxic gas sensor using surface plasma resonance technique, and the list is going on and on and on. I don't have time to read all this, his project, which is a lot. Professor Brian Yuliarto has published many journal articles in high impact journals, and today he will deliver a presentation entitled Application of Metal Organic Framework as Sensitive Layer for Various Biosensors. So ladies and gentlemen, without further ado, please join me to welcome Professor Brian Yuliarto. Prof. Brian, you have 20 minutes to deliver your talk, and then it will be followed by 5 minutes Q&A session. Prof. Brian Yuliarto, the floor is yours. I think Professor Brian Yuliarto is already with us, but probably he's having.
Yes.
Okay, good.
I'm here. Good. Yeah. Okay.
Okay, good.
Can I start to share?
Yes, please.
Wait. Okay, wait for a while.
Maybe the host can help share your presentation, Prof. Brian.
Okay. Yes. Can you see my PPT, PowerPoint?
Yes, it's shown clearly now.
Can you see my PowerPoint?
Yes, I can.
Sorry for it.
That's okay.
The connection is not good here. Several days problem with connection.
Okay, I can see you clearly now.
Okay, can I start now?
Yes, please.
Okay, thank you very much. The official and organizer of second international conference on natural sciences, mathematics application Research and Technology from Ratulangi University. This morning I will give presentation titled Application of Meta-Organic Framework as Sensitive Layer for Various Biosensors. So I think this is honorable for me to be invited here, and the attendance is too many, reach more than 800. So I hope this presentation will give you another insight of nanotechnology for biosensors. So I belong to Institut Teknologi Bandung, Department of Engineering Physics, Faculty of Industrial Technology. As we know that the biosensors actually consist of several parts. We have a transducer here, and then nanomaterials, biorecognition, and amplifier here, microcontroller, the display. The display will explain or will give
Is having technical difficulties again.
Work. Sorry.
Okay, you're lagging.
Can you hear?
It's okay. Yes, it's okay now.
Okay. So sorry, I close my camera, so maybe it will be better.
Yeah, that's probably the good idea.
Okay. So in this work, we will concentrate of the nanomaterials of the sensors. Of course, another researcher will concentrate or can concentrate in many parts of these biosensors. Some of them concentrate in the transducer, some of them in the microcontroller and amplifiers, and another researcher can concentrate on the biorecognition elements. So in this research, we report about MOF. Why MOF? Because MOF is actually electrochemical, the materials, this is the new materials, I think. The previous speaker also groups can report or involve the MOF on the biosensors. So we see that the MOF has advantages. The application, because they have abundant active sites. Also, they have tunable pore and tunable surface chemistry. We see that the application of MOF in biosensor with this or their properties will enhance the performance MOF as biosensors. Okay, and then morphology control of MOF will significantly, we believe this statement that the morphology control of MOF can improve significantly the performance of MOF in the biosensor itself. Because we know that by controlling MOF, basically we induce defect on their surface. Means that the performance of the biosensor will improve, because the function of defect can be as follow, like the defect can open active sites. Also can the function of defect means surface modifications and increase catalytic activity. So now we go to the first case of our development of biosensor using MOF. We perform the hepatitis B virus detections based on MOF. The hepatitis B, as we know that this is one of the very dangerous disease that can cause liver damage and even cancer. In Indonesia, hepatitis B B involve about 28 million people of Indonesian people, including B and C, and 1.4 of them has a potential for the heart cancer. And also WHO reported that about 20 million, yeah, the people in the worldwide were infected hepatitis B virus, caused 887,000 deaths. So the significant problem of health can be handling if we can make easy detection or easy monitoring of the biosensor itself. Okay, so yeah, WHO reported in 2015 about 257 million people were infected. So this is a very big number, and until now, the monitoring is still expensive for hepatitis B. So we try to prepare MOF using that MOF materials, biosensor for hepatitis B. So 3-ethylamine can control Cu-MOF nanosphere with amino functional ligand as biosensing platform for hepatitis B, surface antigen detection. So we make several variations. We add TEA in various concentrations and also PVP. Hopefully we can modify the morphology of the biosensor and we can see what's the effect of the morphology for the sensing performance. Okay, here we can see clearly from these results that when we add several TEA and PVP, the morphology of the biosensor MOF can be controlled, which part that we want. We can control the numbers of TEA. Because TEA was functioned as a pH modulator that strongly determined the nucleation of MOF, and PVP was functioned as a capping agent that can inhibit the crystal growth in a certain direction. So TEA that promoted the deprotonation of NH2 BDC ligand, which resulting a faster nucleation rate, and PVP protects the crystal growth from agglomeration nanosphere structure with relatively good. So you see clearly that there are several different morphology of the MOF. Okay, and we use here a CuBDC. So the absence of PVP leads to the irregular structure of CuBDC, in which the CuBDC particles are severely agglomerated. Based on these observations, the was obtained and was concluded as the best candidate for hepatitis B or HBsAg antigen of hepatitis B. And then we do cyclic voltammogram here. Okay, we can see the cyclic voltammogram was used to evaluate the electrochemical biosensor properties of CuBDC. And we see that without CuBDC, the working electrode of GCE give a relatively high current as a result of redox reaction of the redox probe of FeCN6. And we see that the high catalytic activity of the metal center of MOF decreased the current slightly in spite of insulator property of MOF. Okay, and we see based on DPV, we also perform the DPV technique measurement. It's clearly observed that the delta current increased clearly with the HBsAg concentration here. Calculation around here, and we see that the based on our calculation, the linear detection and limit of detection of our sensor are 1 until 500 nanogram per milliliter which is very wide range, I think. And also the limit of detection is about 0.73 nanogram per milliliter, which is very small, yeah. So we can detect even 1 nanogram in a 1 milliliter serum of ABS-AG. And then, okay. It's slow. Okay. Okay, here we see here. Oh, sorry. From these figures, we can see that the reproducibility of immunosensor was studied by using 5 different modified electrodes prepared with 100 nanogram per milliliter. Okay, we see several times, and the relatively standard deviation of 5 electrodes was found to be very small. It's about 3.24%, confirming good reproducibility of the immunosensor. And also we make the selectivity investigation in figure, comparing DPV signal response of molecule target. So we try for other hepatitis like here, hepatitis D, and then this is the hepatitis A, hepatitis C, and hepatitis B. So we can see here that hepatitis B reveal very high compared to the other hepatitis, indicate that our sensors can detect and select the target rather than, because of course sometimes in our blood, in human blood, there are several others that disrupt or make a noise of our measurement, but our sensor confirm that they can select the target very good. And to evaluate the potential clinical application, we prepare immunosensor to detect certain concentration in human serum samples. So we buy serum from human body, human blood, and we put our immunosensor inside of the serum. We know that the serum, of course, consists of many parts of the protein that can disrupt of the measurement. And after we diluted ABS-AG in the serum samples and incubated to the prepared immunosensor to study the comparison of obtained current response using the calibration method, based on our calculation, the recovery of 95% can be achieved. So I think this is also very good result that we confirm even in this from the serum, our biosensor can give good measurement. Sorry, how long more on my time? I just want to confirm because I will not explain so detailed.
Well, you have more. You have 10 minutes more.
Okay, thank you.
Lots of time.
Okay, so the next one, we develop the M.O.F biosensor for dengue virus detection. As we know that the dengue is one of the also problem, and they spread to all of Indonesian islands. And we have the 3 largest dengue attacks in Indonesia in 88, 98, and 2007. So every 10 years, we will got attack from the dengue. So it's very good and very important if we will have monitoring detection kits. Again, we make some modification of M.O.F using 3-ethanolamine to control the Cu M.O.F morphology for dengue 3 antigen detection. The 3-ethanolamine was used as pH modulator and capping agent in the preparation of Cu-BTC. Similar with the previous case, the presence of TEOA does not disturb the crystal structure of FMIPA since their patterns are similar. However, it was found that the TEOA affect the growth preference of Cu-BTC, where the high amount of TEOA makes some of peak disappearance. So we make variation of TEOA, and we got that the variation clearly can control the morphology. And the morphology, of course, as we talked before, they can control many things to confirm or to improve the biosensor performance. Here we see, in the case of the concentration of TOA involved in the MOF formation at low concentration of TOA, the TOA act as a pH modulator that increase nucleation rate of Cu-BTC via deprotonation of BTC lesion. At this concentration, the morphology of Cu-BTC is octahedron, similar with the common the increasing of TOA concentration to 35 was observed here as shown in the center here. Okay. So the increasing of TOA concentration at 30% was observed can change the morphology of Cu-BTC to mini rod. Interestingly, further increase the TOA not only change the morphology but also decrease the diameter of mini rod. At this concentration, bifunctional TOA, for example, at 40% concentration, the bifunctional TOA acts both as a PM modulator and capping agent. Based on analysis, the mini rod has a diameter of 43 nanometers and length of 100 nanometers. So we continue this result to the measurement of DNV antigen, and of course we put the TA 40% because one-dimensional got in that concentrations, and we believe one-dimensional will have a better sensing performance. And see, one-dimensional Cu-MOF generate the highest current compared to others, indicating higher catalytic activity. So this can be seen by highest generated current in CV and as well DPV mode when their electrochemical properties measured in the presence of redox probes. The one-dimensional structure of MOF, which resulting from the large amount of TOA, about 40%, has advantage in molecular transport, electron transport, high surface area, and abundance open active sites that are available to the surface reaction. So we try also good stability when surface CV measurement was performed after even 10 cycling. And we continue to the measurement of DNV, measurement response. So we can see here the dengue sensing property evaluated with DVP as shown in the left side of in the figure. In the presence of redox probe, the GCE modified by Cu-BTC display high current due to the high catalytic activity of 1D MOF. This proposed mechanism is similar to the previous hepatitis virus. The successful immobilization of antibody on the MOF is marked by the decreasing in generated current due to MOF inhibit the electron transfer. Moreover, the coupling of antibody antigens is also marked by the abruptly decreasing of generated current. This phenomenon and then was supported by EIS measurement where the presence of the antibody antigen increased the impedance, as we can see in the right side of this picture. And here we also measure the different concentrations of dengue from the 0.00 nanogram to 10 nanogram per milliliter as shown here. And this is very good linear, and also in the right side, we confirm again the calculation. We check the electrochemical response by varying, okay, from the 1 picogram per milliliter to 10 nanogram per milliliter. And based on the measurement, the sensor still can detect the dengue antigen down to 1 picogram per milliliter. You can see here, this is very, very sensitive biosensors, because in the previous one, we just got 1 nanogram, but here 1 picogram per milliliter. Okay, so I think that's all my presentation. I just want to show you again that actually we also measure with other biosensor, the uric acid from the M.O.F 71 here. And again, we got the sensor also same, good sensitivity, about 0.4811 milliampere per millimolars per centimeter square, and the detection limit down to 15.61 micromolars for uric acid detection. And for glucose, we also got a result. And even here, we try several metals like Cu, Mn, and zirconia, and also nickel here. And we got that the nickel is one has the highest catalytic activity, resulting the resulting the very good response for the biosensor also compared to other metals with several several metals. Okay, I think that's all. I can conclude some summary for my talk. Metal organic frameworks have high potential to be used directly as a sensitive material for biosensors. The performance of M.O.F itself are determined by its physicochemical properties, including the morphology. The morphology of metal organic frameworks can be controlled by employing modulators such as TEA, TEOA, and PVP. 1D and 2D structure of MOF not only have higher surface area compared to those of 3D structure, but also have abundant active site. That's the more important, I think, in case of biosensor applications. MOF in 1D and 2D structure are proven to have higher performance originating from its high catalytic activity. So that's all. Thank you for my collaborators and of course all of my students who have worked hard to get a good result for our published papers. Thank you. I get back to the moderator.
Okay, thank you. Very interesting talk, Prof. Ryan. We have some questions that have already been posted in the chat room. Can you see the question yourself, Prof. Ryan?
Okay.
Okay, maybe you can respond to the question directly.
Wait, I cannot see.
You haven't seen it? In the
I
chat area?
see, sorry.
You cannot see. Okay, I'll read the question.
There is no chat.
Okay, I will read the question.
Yeah, please.
The first one. What types of organic materials can be used as frameworks?
Okay. Thank you. So the ideas of MOF, metal organic framework, is actually how they can combine the metal and organic. So there are several ligands, as well as there are many metals that can combine to these MOF systems. But the interesting of the MOF is because they have metals and they have organic here. They have and they join to one framework. In this case, because in the application of biosensor, for example, or other sensors, we need the electronic properties of the metals, actually. But if they just only metals, when they make interactions with the target, as we know, the biosensor, of course, have the target for many organics like protein, like as I explained, glucose, protein, dengue, or even COVID-19, for example. That's the target is actually organic. But in case of pure metal, there is no place for interaction between the target and the metals. So the MOF facilitate these conditions because the MOF consists of metals and organic. So many organic can be prepared for, of course, MOF. but we have to make sure in the application of MOF and application of biosensors, we have to find the organic that can make interactions with the target of biosensor of the biomolecules, and they also can make interaction with the metals. So that's the key for the organic that we have to use in the more for biosensor application. That's, I think, I hope you can explain by my answer. Of course, I'm very open to make a further discussion.
Okay.
Yes.
Thank you. And the second question is, can all metals be used as sensors?
Can what? Sorry?
Can all metals, all kinds of metals?
Yes, I think nowadays so many metals already tried to make biosensor or other sensor or chemical sensor, for example. But again, it depends on how their catalytic activity. So how can the metals can be influenced? Their electronics properties can be influenced by the organic that attach to the metals, and these organic materials have interaction with the targeted biomolecules. So when the biomolecules interaction with the organic, and of course this organic is connected to the metals, so how good these organics, the interaction of biomolecules and the organics can influence or can change the electrical properties. That's we find. Of course, I think all metals have changing in their properties, in their electrical properties, when the biomolecules and organic have interaction. But the question is, or what we need is the biggest changing in electrical properties means much better for us, because when the changing of electrical properties is big, so means that we can detect very low detections in sensitivity. That's we want to find. If the changing is only very big, little, very small, will be biased for us, because yeah, of course, when the sensitivity is very small, sometimes we will not know how big that biomolecules that we detect. That's the problem. Okay, I hope it can answer the question.
Okay, I do have a question on my own, because my background is molecular biology, and I've seen you use aptamer RNA in one of your projects for LSPR-based detection of COVID-19, because it's very relevant to current situation, pandemic, right? So could you please share a little bit about the story of this COVID-19 detection using aptamer RNA?
I'm sorry. I'm not so familiar with that case. Quite different.
Okay.
But LSPR is very interesting technique. Actually, we also developed some technique for COVID-19. But I can inform. I can explain here that the electrochemical technique is actually quite different with the LSPR technique, and also we develop other technique named SPR, surface plasmon resonance. There is LSPR, there is SPR, and there is electrochemical. The electrochemical, of course, based on the electrical property changing when the chemical reaction means biological, of course, include in this reaction. So the interaction, biomolecules and organic framework change or influence the electrical properties. LSPR means that depend on the optical properties. So it's quite different. The interesting one for LSPR is very easy technique, and also I think this is very accurate technique. The problem is how we find the optical materials, optical property material, which is very good changing when there is interaction between targeted like COVID-19 with the the solution of the materials, which I think the gold will be very good, and the gold modified with other metals also, I think will be very interesting, professors. Sorry if it's not answered the question, but that's I can explain to you about Elsevier.
Okay, thank you very much, Prof. Brian. I think there are so many questions that the participants want you to answer, but since we are limited in time because there's a second part of the session of plenary speak, we have 3 more plenary speakers upcoming.
Thank you.
So I have to end. So unfortunately, that answer from Professor Rian Yuliarto concludes the plenary session for this morning. Thank you very much, Professor Rian Yuliarto. Ladies and gentlemen, finally, we come to the end of the presentation of this part of this session. On behalf of the Icon Smart Organizing Committee, I would like to say thanks again for all the presenters for their informative, interesting, stimulating, and thought-provoking presentation, and to audience for your active participation. Hopefully the presentation will be beneficial for everybody. Thank you for your attention. Since we will continue to the second session, we still have 3 more plenary speakers. I will hand over the floor to our MC,